Good day. Today we're going to talk about double integrals over general regions. I think this is the last video in this series, and I hope you've been enjoying and learning through all of these lessons. I just also want to say that I'm a little bit under the weather today, so if I have a little bit less energy or perhaps my voice is a little bit lower or scratchier, it is mostly a reflection on a long but good quarter working with all of you. So hope you enjoy this lesson as we bring things home with the beautiful topic of double integrals over general regions. Double integrals over general regions. Before we get into the why, let's do the following example to get a taste for the how. Example 1. Let's evaluate the double integral from 0 to pi and 0 to cosine of y of x sine y dx dy. Notice that this is an iterated integral. We have limits in our, we actually have limits or bounds in our integrals, but notice also that there is a variable y in one of these limits of integration. So without trying to overthink it, let's just work through this question and see what happens. So if we want to treat this like we did in the previous section with iterated integrals, we're going to start by focusing in on this intersection. And so we'll have that outside integral 0 to pi and the dy in place. And then inside that, we'll have the antiderivative of x sine y with respect to x will be x squared over 2 times the sine y. And then we're evaluating this from x equals 0 to x equals cosine y. So this will be, so here's all that yellow stuff is becoming this, this expression here. So this is equal to the integral from 0 to pi of, it looks like when we put in 0, we're going to get out 0. And so we're just going to have 1/2 cosine squared y sine y dy. Here, I think we can see that you could do a substitution. We might have to mess around with our signs a little bit, but it should be pretty straightforward. So this will be equal to the cosine cubed of y. And when you take the derivative of cosine cubed of y, you'll get 3 cosine squared y. So we'll have the 1/2 from before, a 1/3. And then the derivative of cosine is negative sine. So we need to negate this term. And then we're going to evaluate the whole thing from y equals 0 to y equals pi. So let's see what that is. So this would be negative 1/6 times the cosine of pi, which would be negative 1, but cubed. Negative 1 cubed minus the cosine of 0, which is 1 cubed. And so that'd be -1, -1 or -2 times -1/6, or positive 2/6, positive 1/3. So not terribly difficult. Notice it's the same thing that we did before. The primary difference being that here we have a function in one of our limits of integration. We don't quite know what that means or what that looks like, how it all works together yet, but it's not that difficult to do the how of it if we can actually get our iterated integral set up nicely. In the last section, we saw how to use double integrals to find the volume bounded between a multivariable function and a rectangular region R in the plane. And that'd be the XY plane. In this section, we'll look at more general regions that are not rectangles. We'll label these more general regions D. And to do this, we will suppose that D is a bounded region and can be enclosed in a rectangle R. Let me make sure you see what's going on here. So here is our region D. That's our D, and it's bounded within the rectangular region R. So here's the R, here's the D. Okay. And from here, the process is very similar. We'll divide D into those small rectangles. Here are those small rectangles, right? Boom, boom, boom. Okay. So we divide them into the small rectangles. Note that at the edge, we have non-rectangular shapes. Those non-rectangular shapes, those would be the ones that are kind of like right at the edge or boundary, but that's okay. Since we're just approximating, we can sort of see what's going on with our Riemann sums. Then we find the volume of each rectangular cylinder. The rectangular cylinders, those are these puppies here. And we add up the volume of all those rectangular cylinders, letting the size of the bases go to 0. Let's look at a couple of manipulates to make sure you're tracking what's going on here. So here is our rectangular region R. So that's the R, and then the inner region here, this is our D. Okay. And we're going to take that the funky shape region D in the middle, and we're going to split it up into a whole bunch of rectangles. Obviously, the approximation of filling out that space will get better and better as we use more and more rectangles, right? And in particular, notice that the stuff on the edges, kind of this stuff here and here, the purple doesn't show up very well. Let's see if the yellow works. Yeah, yellow doesn't work very well either. How about red? Okay, the stuff in here on the edges, like those little teeny bits that are missed, get smaller and smaller as we take the number of rectangles toward infinity. In the limit, as we let the size of those rectangles go to 0, you can see that there's no longer any gaps right there on the edge. So once again, we took our rectangle R. Inside our rectangle R, we have a space that we're calling D. In our notes here, they're kind of labeled backward. And above each one of these rectangles, we're going to draw a little tower, a rectangular prism, if you will, that goes all the way up to the surface above. And so you can see that the bases all line up with the bases in that region, and then the tops are going up as far as the surface is concerned. Here, it looks like, instead of taking arbitrary points, it looks like maybe we're making sure our graphs match, like on one of the corners or something. It's a little unclear what's happening there. If we want to make our approximate volume, the volume made by adding up all the little blue volumes better, we could increase the number of rectangles. Notice as we increase the number of rectangles in the base, everything just gets a lot prettier, a lot smoother. And in the limit, as the size of those rectangles goes to 0, we get our double integral representing the actual volume of the solid. So that'd be between the surface up above and the XY plane below. So it's pretty much a direct extension to what we did back previously in calculus, a direct extension to what we did in the previous section where we introduced double integrals. The big difference here is that our regions, kind of our domains that we're integrating over, are no longer rectangles. That's the big excitement here. So to find a better approximation, we'll increase the number of the rectangles to infinity, which takes us to the double integral definition of volume. That is, that the volume is equal to the double integral over the region D Well, it's kind of interesting. We've got our D's and our R's. A little confused here. I think this would be this is a D here. The double integral over the region D of f of xy dA. Plane regions can be extremely complex. Let me make sure you're understanding what's saying. A plane region, that would be the funky shape that's the base. So plane regions can be extremely complex, and the theory of double integrals over very general regions is a topic for an advanced course in mathematics. We're going to limit our study of double integrals to two basic types of regions. A type 1 region is bounded on the left and right by vertical lines. Let's see. So bounded on the left and right by vertical lines, that would be here and here. And that's x equals a and x equals b, and it's bounded below and above by the continuous curves y equals g1 and y equals g2 of x. So bounded below and above by g1 and g2. So here's our g1, here's our g2. So then the double integral d of f of x y dA, that is the double integral without any built-in method for integration, is equal to the iterated integral from a to b, integral g1 of x to g2 of x of f of xy dy dx, where d is equal to the set of all xy's such that a is less than or equal to x is less than or equal to b, and g1 of x is less than or equal to y is less than or equal to g2 of x. Since x is fixed for the first integration, we can draw a vertical line in the region right here. The lower point of the intersection is the curve y equals g1 of x, and the higher point is at y equals g2 of x. These are the lower and upper y limits of integration. And notice those arrows that I drew start on the left at x equals a and move on the right to x equals b. So that's called a type 1 region. You don't need to memorize the name of this. That's not the kind of thing, but what is really important is the picture and understanding and of how the picture and the integral connect with each other. A type 2 region is bounded below and above by horizontal lines. Below and above by horizontal lines, that would be here and here. And that's y equals c and y equals d, and is bounded on the left and right by the continuous curves x equals h1 of y and x equals h2 of y. So that would be these curves here, there. So then the double integral across the region D of f of xy dA, and again, this is a double integral without any built-in method for calculating, can be written as the iterated integral. Now we do have a method. It's the double integral from c to d of the integral from h1 of y to h2 of y of f of xy dx dy, where d equals the set of all xy such that h1 of y is less than or equal to x is less than or equal to h2 of y, and c is less than or equal to y is less than or equal to d. Since y is fixed for the first integration, we draw a horizontal line in the region. So here's that horizontal line in the region. So these would be these arrows coming left to right. The leftmost point of the intersection is in the curve x equals h1 of y, and the rightmost point is on x equals h2 of y. These are the lower and upper x limits of integration. So notice that the red lines here, the arrows, if you will, are parallel to the x-axis. And that x-axis there that's the same as that inner letter in the dx. If we go above, here our arrows are parallel to the y-axis. And again, that y is this matches the inner limit of integration. There you have the basic gist of type 1 and type 2 regions. Example 2. Evaluate the double integral of 2x squared y dA over the region enclosed between y equals 3x squared and y equals 16 minus x squared between x equals 2 and x equals negative 2. There's a typo here. X equals plus or minus 2. So let's start by drawing the region D. So we're going to draw the region. So we have a some sort of a grid, and notice that there is a smiley parabola here. So this would be the y equals 3x squared. And there's also a frowny parabola. This would be at 16. Okay. And this would be y equals 16 minus x squared. We need to find these points of intersection, specifically the x values of those points of intersection. And so we could solve for where 3x squared equals 16 minus x squared. So 4x squared equals 16. X squared equals 4. X equals plus or minus 2. So here we are at minus 2, and here we are at positive 2. And so our region is enclosed between these two critters, and so it looks like our region is, not surprisingly, the football-shaped region in the middle. So the next thing we want to do is set up an iterated integral. Before we set up an iterated integral, we've got to decide whether or not we want to integrate horizontally or we want to integrate vertically. And what I would point out is that if you integrate horizontally, then you are going to start on one curve. So we'd have some x value, and you'd end on the same curve, which is a little bit difficult. It's not impossible, but that would mean you'd have to split each one of those curves into a couple of pieces, and also things would change if you were on the top of the football versus the bottom of the football. So instead of taking that approach, let's integrate vertically. And so I'm going to draw a whole bunch of these arrows through my region. Okay. And I can see that the arrows all begin, like the bottom of the arrows is all here on y equals 3x squared. And the top of my arrows is all ending on y equals 16 minus x squared. So with that in mind, the next thing we can do is we could set up our iterated integral. Set up the iterated integral. So that double integral, and maybe we could call it, let's give it a name here. Let's call it I for integral. So we're saying that I, our integral, is going to be a double integral And we're going to start at, the integrand is going to be 2x squared y, and we're going to start on the bottom, which is yellow, or at y equals 3x squared. And we're going to go to the top, which is at y equals 16 minus x squared. Let's get our colors in there. Okay. And we notice that the left arrow is at x equals -2, and the right arrow is at x equals 2. So notice that we integrated first with respect to y. We're parallel to the y-axis, so all of these arrows, all these arrows are parallel to the y-axis, so we have a dy, and then that means our outer limit is going to be dx. So we're going from left to right. Left to right. Now we just need to evaluate the integral and see what happens. So we start by evaluating the inner part. So this would be the integral from -2 to 2. That part stays the same. And I'm going to start my bracket. Integral with respect to y would be x squared y squared from y equals 3x squared to y equals 16 minus x squared. And we still have a dx sitting out here. Plug and play with your fundamental theorem. So this will be the integral from -2 to 2 of x squared. That's going to be a constant. And then I'm going to put in the 16 minus x squared squared minus 3x squared squared dx. Now we're left with an integral that is just in terms of x. So it looks like we're going to have a little bit of work to figure out what these puppies are. So notice that 16 minus x squared squared would be 256 minus 32x squared plus x to the fourth. And 3x squared squared would be 9x to the fourth. So we have a total of the integral from -2 to 2. That looks like 256x squared minus 32x to the fourth. And then I have x to the fourth minus 9x to the fourth, so that'd be minus 8x to the fourth. In this case, I'll have minus 8x to the sixth dx. Put parentheses around that whole integrand. These values are all even, or these functions are entirely even, symmetric around the around x equals 0. There's also a common factor of 8. So maybe I will ignore that. So I've got integral from 0 to 2. And then because it's even, I'm going to double it. So make my anti-differentiation a little easier. So now I have 256x squared minus 32x to the fourth minus 8x to the sixth dx, which would be 2 times, it looks like we have 256 over 3x cubed minus 32 over 5x to the fifth minus 8 over 7x to the seventh, evaluated from 0 to 2, which, let's see, I think I can do this one with my Texan friend. So let's see, what do I have here? So I have 2 times 2, 56, times 2 to the third, divided by 3, minus 32, times 2 to the fifth, divided by 5, minus 8 times 2 to the seventh, divided by 7, which is, it's an ugly fraction, but it's just a fraction. 69632 over 105, or about 663. And so our question was pretty simple. We needed to evaluate the integral. To do that, we drew our region D, then we set up and evaluated our iterated integral. Let's look at a couple of manipulates to try to make sure we understand the picture of what's going on in this question. So here is our region D that we drew. And notice those arrows are starting at the red curve and going to the black curve. And we're moving along. There's the blue arrow at the bottom that's representing the fact that we're working from x equals -2 to 2. And then the orange arrow is telling us our starting and our ending value for our inside limits of integration. Here's this same picture, but now in 3 dimensions. So if we look at it in 3 dimensions, notice that as we move along our x, our inner limits, we still have the orange going from lower red to upper black. We're moving along the blue, and then for each one of those values, what we're doing is we're asking what is the area of this cross section, kind of multiplying it by the width. And so we're saying if we add up all of those little areas and we take each of those areas times the differential width, which would be a dx, that would give us our total volume. In this case, we're saying that the total volume underneath this surface above that region would be about 663. Example 3, evaluate the double integral over d of 2 plus 1 over y dA over the region enclosed between y equals 8 minus x, y equals x, and y equals 1. So again, our first step is to sketch the region. So let's see, y equals 8 minus x would be a line with negative slope. Y equals x would be a line with positive slope. And y equals 1 would be a horizontal line here. So it looks like the region that we're interested in is the yellow region in the middle. Notice we could run our arrows vertically like before, but if we run vertically, notice that the ones here on the left side go from the horizontal line up to y equals x, while the ones on the right side go from y equals 1 up to y equals 8 minus x. So it's changing partway through. That's too complicated for us. We'd like to avoid that situation if we can. And so we will, come on, baby. We will run, instead of going vertically, we're going to run horizontally. So I'm going to draw a whole bunch of arrows, horizontal arrows. And you'll notice that these arrows have a starting point, that they're all parallel to the x-axis. So we want to think about them as having an x value. So they all start here at an x value, like x equals y. And they have an ending value over here. Again, we're parallel to the x-axis. So we want to think about what is x equal. of x equals, it looks like 8 minus y. So we're going from the yellow, this will, instead of having a bottom, in this case we'll have a left, to the green, which is x equals 8 minus y. Okay, so we sketched the region. So next we're going to set up and evaluate our iterated integral. So we have this double integral. Maybe this time we'll write it. So I have the double integral over d of 2 plus 1 over y dA is equal to the double integral. And here we're going side to side. So we're going from x equals y to x equals 8 minus y. That's from yellow to green of the integrand, which is 2 plus 1 over y. And we're going to go dx first because we're parallel to the x-axis. And then our y values, our lowest arrow is at y equals 1. And our highest arrow, I don't think we found this point. We got to find this intersection point. Where do they intersect? So we could set y equal to 8 minus y. So this is, that's a y, not a g, sorry. So this is yellow equals green. Set the two equal to each other. So that would be 2y equals 8 or y equals 4. So we're going to go from y equals 1 to y equals 4. And this is dy. Because our inner limit says our arrows are going parallel to the x-axis. Our outer limit, or our second dy, tells us that we are running those arrows, like all those arrows are sort of intersecting the y-axis back here. So y equals 1, y equals 1.5, all the way up to y equals 4. Something like that. Now we just need to evaluate and see what kind of good things come out. So notice that we are integrating with respect to x. So all this garbage is a constant as far as x is concerned. I'm going to go from 1 to 4, and then we'll have x times 2 plus 1 over y dy. We're going from x equals y to x equals 8 minus y. So let's see. So that would be the integral from 1 to 4 of, we're going to have 8 minus y. So I've got this 2 plus 1 over y. And then I'm going to have an 8 minus y dy. Let's see. This is 8 minus 2y. Okay, so if I multiply all that stuff out, I would have integral from 0 to 4. So I'm going to FOIL, so I have 2 times 8 is 16. 2 times minus 2y would be minus 4y. 1 over y times 8 would be plus 8 over y. 1 over y times minus 2y would be minus 2. and all of this is dy. Let's see, I'm thinking there's a common thing here. I've got a -2 and a +16. That's a 14 altogether. So my antiderivative at this stage would be 14y minus 2y squared plus 8 ln y. We want to evaluate from 0 to 4. So if I evaluate from 0 to 4, golly, 14 times 4, I think, is 56. So I have 56. 16 times 2 is 32, plus 8 ln 4 minus 14 plus 2, and the ln of 1 is 0. So let's just check these constants. So I have 56 minus 32 minus 14 plus 2 is 12. So altogether, I've got 12 plus 8 ln 4. And that 12 plus 8 ln 4 would represent the volume of the region under z equals 2 plus 1 over y and above the triangle that we talked about earlier. Let's look at a couple manipulates to try to make sure we're seeing what's going on. So here's the region that we care about, the triangular region. Notice that our arrows are all running, the blue arrows are all running parallel to the x-axis. So that tells us that we're going to have a dx as our inner limit of integration. The lowest blue arrow is down here where at the orange y equals 1. The highest blue arrow is going to be at the top of the orange arrow where y equals 4. That's going to tell us our upper and lower limits for the outer limit of integration. So here's our region. Let's take a look at a second manipulate where we can visualize the solid. So here is the solid we're looking at. Below you can see the triangle. Above, here would be the surface, z equals 2 plus 1 over x. And you'll notice that as we cut along, we've got kind of this plane region, the square, if you will, that's sweeping through. We're saying these are our areas. We'd multiply them by a thickness, which is a dy, and that would give us our total volume. Here's the total space. So we went from y equals 1 all the way up to y equals 4. All the regions in between. So historical note. Our definition of the definite integral is based upon the work of the German mathematician Bernhard Riemann, who was born in 1826 and died at the age of 40 in 1866. The son of a pastor, Riemann's plan was to become a minister like his father. However, he was just too good at math to set it aside. So when he arrived at university, and with his family's permission, he began to study under Carl Gauss, the same mathematician you've heard of before, that Gauss. His work as one of the key contributors to the rigorization of mathematics remains very influential. Personally, Riemann, again, this guy that was the one that helped us come up with our Riemann integral and our Riemann sum, personally, he was shy and he suffered from numerous nervous breakdowns. He had a terrible fear of public speaking. He was also a perfectionist who wouldn't publish anything unless he felt it was perfect. Story goes that some of his unpublished papers were discarded by a maid who did not realize their potential value. He died in Italy, having had to flee war in Germany. One thing I appreciate about the story is he was an interesting character, and he reminds us that we don't have to all fit the same box if we want to be successful as mathematicians or as engineers or computer scientists. Back to Riemann. While he did not pursue the ministry, Riemann remained dedicated to his faith for his lifetime. He saw his work as a mathematician as another way to serve God and considered his faith the most important aspect of his life. This tombstone ends with the inscription, "For those who love God, all things must work together for the best." So there's a little bit about Bernhard Riemann, the one for whom our Riemann sums and our Riemann integral is named. Example 4. Use a double integral to find the volume of the tetrahedron bounded by the coordinate planes and the plane z equals 4 minus 4x minus 2y. And so what we're going to do to begin with is we're going to try to sketch this, this curve and see what happens. So here's our x, our y, and our z. And if we let x and y equal 0, x equals y equals 0, then you can see that z would equal 4. Would be a point on the surface. And if you let your x and your z equal 0, then let's see, x and z equals 0, you'd have 0 equals 4 minus 2y, or y equals 2. Right there. And if we let our y and our z equal 0, then that would be saying like 0 equals 4 minus 4x, or x equals 1. There's the 1. Comes out right here. And so our surface in the first octant would look something like this. Okay, so the first thing we did here was we sketched a picture that gave us a clear view. And now we're going to try to focus in on the region that we're integrating over. So we look on the xy plane. So here's x, and here's y. And we notice that our y is going through y equals 2. Our x is going through x equals 1. And so our region is this triangle in the first quadrant. This would be the volume of the tetrahedron bounded by the coordinate planes. That would be the xy plane, the xz plane, the yz plane, and the given plane z equals 4 minus 4x minus 2y. So here's our triangular region. In this particular case, let's see if we can find the equation of our line. So it looks like our line has a y-intercept of 2 and a slope of -2. Okay, and notice that we could go horizontally or vertically, but since I've already got it written as y equals, maybe we'll work vertically here, draw a whole bunch of vertical arrows. And so notice those are all starting at y equals 0 down here. And they're all ending on the line y equals 2 minus 2x. I didn't label the step. Again, this is all the first step, which is find the region or sketch the region. Okay. Step 2 is to set up and evaluate our iterated integral. Evaluate the iterated integral. So here we would say our volume will be equal to the integral. My lower limit is going to be from y equals 0 to y equals 2 minus 2x. This is from the blue to the green. And my arrows are running. The leftmost arrow is at x equals 0. The rightmost arrow would be at x equals 1. And notice that our arrows are running parallel to the y-axis. So I'm going to go dy and then dx. And our only question is, what is the integrand in this case? So since we are looking for volume, and we want the volume underneath that curve above, then we can just simply fill in the plane that we were given, namely this one here. So we'd have 4 minus 4x minus 2y. And that will be our iterated integral. At this stage, we just have to evaluate it and see what good things happen. So this will be the integral from 0 to 1, and then bracket. Antiderivative with respect to y would be 4y minus 4xy minus y squared, from y equals 0 to y equals 2 minus 2x. And all this is dx. So if we put in y equals 0, everything is going to come out at 0, so that part's nice. So we have the integral from 0 to 1 of 4 times 2 minus 2x minus 4x times 2 minus 2x minus 2 minus 2x squared, all that jazz, dx. So it looks like we have a little bit of algebra to do. So all of this stuff together would be, see, we have 8 minus 8x minus 8x again, plus 8x squared minus, oh, I gotta remember that minus sign. So 2 squared is 4, minus minus or plus 8x for the middle term, minus 4x squared for the last term. So if I combine like terms, this would be the integral from 0 to 1 of 8 minus 4 is 4, minus 8x minus 16x plus 8x, so minus 8x, and plus 8x squared minus 4x squared, so I have plus 4x squared, which would be home stretch. So I have 4x minus 4x squared plus 4/3 x cubed on 0 to 1. At 0, all these are going to be 0, and so we'll have 4 minus 4 plus 4/3, or just 4/3. So we're saying the volume of this tetrahedron would be 4/3. And there's probably a formula for that, but I don't remember it off the cuff. So we probably could know that it was going to be 4/3 just using geometry from the dawn of time. Let's look at a couple of manipulates just to make sure you're, again, seeing the picture of what's going on. So here is the tetrahedron that we're talking about. Okay, and notice in this case, we've done it with A's, B's, and C's. But this is a pretty common shape because it's one of the few three-dimensional objects that's pretty easy to draw. So maybe get used to drawing one. It's probably one of the, not the only one, but one of the few types of 3D surfaces I might ask you to draw, say on an assessment or final exam. So that's pretty straightforward. And I think I have another manipulate here. So once you have that tetrahedron, then you can look at the base of it. And here, notice you could go side to side if you wanted to. So you could run your orange arrows side to side, but it tends to be easier for us to start by going dy, simply because we're used to thinking about this black line here. Like, it's the fact that this black line is easy to write as y equals some mx plus b. Like, that's what it is that makes it so we tend to go vertically versus horizontally in this particular case. So pretty easy to find the volume. Takes a little bit of doing. You just gotta follow through and be careful. Example 5. Find the volume of the solid bounded by the cylinder x squared plus y squared equals 4, and the planes y plus z equals 4 and z equals 0. So as with the previous example, we're going to try to draw a rough sketch to try to understand what's going on prior to figuring out what our region looks like. So let's see. So x squared plus y squared equals 4 is a cylinder, and it would be a vertical cylinder looking something like this. We don't have our axes in place yet, but they would run right through, the z-axis would run right through the center of the cylinder. And y plus z equals 4 is going to be a plane. And let's see, what's that plane going to look like? So if it goes through, if we think about that, like z equals 4 minus y. So if it goes through 4, here's y, and here's y equals 4. Looks something like that. Okay, and let's see. Find the volume of the solid bounded by this cylinder and the planes, and z equals 0. So it looks like what we have, so we want to be bounded completely by it. So it looks like we have a surface that has like a oval top and a circular base. Something like that. So here is the z-axis, the y-axis, x, and this surface here will be z equals 4 minus x. The one at the base will be z equals 0. And then the sides are the x squared plus y squared equals 4. So that's the shape that we're working on. Now that we have figured out the shape, oh, and I should comment that this would be 2 on the x and the y, because the radius of that cylinder would be 2. So we can now set up we can now draw a picture of our region that we're trying to describe. Sorry, I'm making a mess over here on this end. So let's see. So if we want to sketch the region, hope it's clear that the region will be this circular region here. Radius 2. And we're going to skewer that region. We could go left to right or up and down, but it's probably easiest for us to go up and down. So you can think about all these arrows shooting from the bottom to the top. And the lower part of this would be where y equals negative square root of 4 minus x squared. That's the lower part. And then the upper part would be where y equals plus square root 4 minus x squared. Something like that. All right, so we sketched our region. Again, we're starting at y equals, and in case you're wondering where those are coming from, we had x squared plus y squared equals 4, y squared equals 4 minus x squared, y equals square root of 4 minus x squared. But when you take the square root of both sides, you pick up a plus or minus. So the plus would be the top half, the minus would be the bottom half. In a future calculus class, you'll learn to use polar coordinates to solve this, and it'll actually be quite a bit easier. But here we're going to have some roots in our limits of integration. So we have our region D. We have our integrand. So now we should be able to set up our iterated integral. So, 2. Set up and solve. We're going to evaluate iterated. Set up and evaluate. An iterated integral. Iterated integral. Okay. So we know that our double integral across the region D would be this whole space here. And our integrand is going to be 4 minus y, because z equals 4 minus y, dA. And so for us, this is going to be a double integral. And we're going to go from the lower limit of y equals negative root 4 minus x squared to y equals plus root 4 minus x squared. So that's from the yellow to the blue. And our integrand is going to be 4 minus y. We're going to go dy because our red arrows are parallel to the y-axis. And then dx. And notice that our leftmost arrow hits at x equals negative 2. And our rightmost arrow hits at x equals 2. So we have set up a double integral quite nicely here, specifically an iterated integral. So now we got to evaluate it. Good news, it looks like some of these radicals might go away for us. So let's see. So this will be the integral from negative 2 to 2 of 4y minus 1/2 y squared from y equals negative square root of stuff. Square root of 4 minus x squared to y equals plus square root of 4 minus x squared under the radical. And all this is dx. So let's see. So when we evaluate this, we will get integral from negative 2 to 2 of 4 root 4 minus x squared minus 1/2 y squared. It'll kill the root, so I'll have 4 minus x squared minus And then we have, when we put in the negative, we'll have a minus 4 root 4 minus x squared. And we'll have, I'll put in the negative here, the negative will die, so it'll still be minus 1/2 4 minus x squared. And all this is dx. Looks like we need a little bit more space here. Okay, so we got a little more space. Okay, let's see what we have here. So we have minus 1/4 or 1/2, all that stuff, minus minus, so plus, plus, all that stuff. So those are going to cancel out. And then we have 4 root 4 minus x squared plus 4 root 4 minus x squared. So it looks like we have altogether the integral from -2 to 2 of 8 root 4 minus x squared dx. We could evaluate this using trig substitution. I believe we could use an arc sign in this particular case, but we could also recognize that this is equal, that this bit right here is the top of a circle, top of a semicircle. Like this. So here's 2 minus 2, y and x. And so it has radius equals 2. And so it has area equal to pi r squared divided by 2, because it's only half of a circle. So it's got an area of 2 pi. So this thing would be equal to 8 times the integral from -2 to 2 of 4 minus x squared dx. All of this stuff here is 2 pi. And so our sum total for the whole thing is 16. So there is our full derivation of finding the volume of the solid between the two surfaces and captured within the cylinder. Example 6, evaluate the integral from 0 to 2 of the integral from y over 2 to 1 of e to the x squared dx dy. At first glance, this looks easy because it's already written as an iterated integral. But when we hone in on the first antiderivative and we go, we need to find the antiderivative of e to the x squared dx, we remember that this particular antiderivative does not have a closed form. Unless we're wanting to bust out our Maclaurin series, there is not an easy, or there isn't a way of evaluating this integral. So we're going to do something clever. What we're going to do is we're going to try to reverse the order of integration using Fubini's theorem. But in order to do that, we need to first draw the picture. We got to figure out what region is represented here. So what do we mean by that? What we mean is that if you look here, we're saying that the x's live between 1 and y over 2. And we're saying that the y's live between 0 and 2. So let's see if we can figure out what this looks like. So try to sketch the region. let's see. So we know y equals 0 and y equals 2. So y equals 0 here. Y equals 2 here. And then we know x equals 1 would be here. And we know that also here you could have like x equals y over 2, which would be the same thing as y equals 2x. And so that would be this over 1 up 2, y equals 2x. So when we were in the way the graph is described with the dx dy, what it's saying is we want to graph horizontally first. But what I'm telling you is because we can't find the antiderivative of e to the x squared, we need to switch this up and integrate vertically. So we're going to draw a whole bunch of arrows from top to bottom. So notice that our bottom is, not that. Our bottom is x equals 0, and the top is here, y equals 2x. So all of our arrows start at y equals 0, and all of our arrows end at y equals 2x. We're going to go, a left endpoint is going to be at x equals 0, a right endpoint is going to be at x equals 1. And let's just double check that we didn't grab the wrong region. So I want to make sure that, just to double check, what if I had this point here? Make sure I didn't grab the other, it's not the other triangle. So if it was the other triangle, say this would be like the point 1/4 and 1. So if I try 1/4 and 1 and I put it in here, the y's would work. But if I put 1 in for y, I'd have 1 over 2 is less than or equal to 1/4. Nope, that would fail. So that did not work. So we checked to make sure that we had the right region, and sure enough, it is the region that I've drawn. Okay. Get rid of some of those things. So we sketched our region. Next up, we need to set up an iterated integral. So to set up and evaluate the iterated integral. Okay. So originally we had the iterated integral from 0 to 2, y over 2 to 1, e to the x squared, dx dy. And now we're saying that this is equal to the integral from y equals 0 to y equals 2x. So this is from yellow to green of the e to the x squared. But now it's going to go dy because we're parallel to the y-axis dx. Our x's are going to go 0 to 1. So let's see how this works out. Antiderivative of e to the x squared with respect to y is just going to be the integral from 0 to 1 of y e to the x squared. Pardon me, from y equals 0 to y equals 2x dx. At 0, it's going to be 0. So we have the integral from 0 to 1 of 2x e to the x squared dx. Here you can imagine letting u equal x squared, and then your du is going to be the 2x dx. So this is simply going to be e to the x squared, evaluated from 0 to 1, which will be e minus 1. So as I foreshadowed in a previous lesson, we were able to take an integral that was impossible to evaluate one direction, change the direction, change the order of integration using Fubini's theorem, and it turns into a pretty easy to evaluate integral. Properties of double integrals. The following properties can be proven just like we did in a previous calculus class. So we have that the double integral of a sum of two functions is equal to the double integral of the first function plus the double integral of the second function. And so here the key is you have this, the double integral of a sum is the sum of the double integral. In the next one, you have the double integral of a constant times a function is equal to the constant times the double integral of the function, again, where c is the constant. Here, the key thing is that scalars can come out front just like they have in the past. Although double integrals arose in the context of calculating volumes, they can also be used to calculate areas. For this purpose, we consider the solid consisting of the points between the plane z equals 1 and the region D in the xy plane. The volume of this solid is v equal to the double integral with integral 1 dA, or just the double integral across d of dA. However, the solid has volume, the area of the base times the height, where the area is of the base is the area of D, the height is 1, so we just get the area of D. I don't think we need this, however. Therefore, we would have that the area of D is just the double integral across D, dA. A pretty easy formula to set up, and we'll use it multiple times, so it's one that's worth remembering. Let me just show you a picture of this before we continue. So here, we're trying to find the area of the region. It's labeled as R here. And so what we're going to do is we're going to create a solid that has height 1. And so the double integral would give us the volume of the solid, but the volume of the solid would be the area of that base that we're interested in times 1. And so there's kind of a funny unit thing. This is the kind of stuff that you can do in math. So the double integral would give you like cubic units, but we know that the cubic, it would be 50 cubic meters for this volume, but we know that 50 cubic meters is over a surface that has height 1 meter, and so we know that the base has an area of 50 square meters, something like that. So pretty easy to work with, pretty easy to use, and definitely one that's worth remembering. Example 7, use a double integral to find the area of the region enclosed between the parabola y equals 1/2 x squared and the line y equals 2x. So here, let's start by drawing a picture. Pictures are our friends. And so we have y equals, ooh, that's a pretty ugly looking parabola. It's not very symmetric. We have y equals 1/2 x squared. And then we have here y equals 2x. And we're looking for the area of the region. We're looking for the area that's bounded in the middle. And you'll notice that the lower part would be the y equals 1/2 x squared, while the upper part, maybe I'll use black. The upper part would be y equals 2x. And so we're looking for area. We could do this using, our old-fashioned Calc 1 methods, but we're in Calc, or sorry, I guess that's Calc 2 methods, but here we're going to use a double integral. And so we are going to set up and evaluate an iterated integral, set up and evaluate iterated integral. So we'll say that our area is equal to, oh, we got to draw our little arrows. We know we're going to go bottom to top. And so we're going to go double integral from the lower one, y equals 1/2 x squared, to y equals 2x. And my integrand, because I care about area, my integrand is going to be just 1. And then we'll go dy because we're running arrows parallel to the y-axis. And it looks like we still need to figure out where these two curves intersect. We need to find this x value. So we could solve 2x equals 1/2 x squared. That would be 4x equals x squared. Or let's see, 0 equals x times x minus 4. So it looks like that's an x equals 4. So I'm going 0 to 4. So I have my area double integral set up. Now we can just evaluate it. So this will be integral from 0 to 4. And then the antiderivative will be 1 of 1 will be y. Going from y equals 1/2 x squared to y equals 2x dx, or the integral from 0 to 4 of the top function 2x minus the bottom function 1/2 x squared dx, which would be, let's see, 2 over 2 x squared minus 1 over 6 x cubed from 0 to 4. Both are going to be 0 at 0. So we're going to have 16 minus 4 cubed is 64, 64 over 6, which would be the same thing as 32 over 3. So that'd be 48 over 3 minus 32 over 3, or 16 over 3. So what we're saying here is that the area of this region here is 16 over 3. And one thing I want to point out is that at this stage, when the double integral is gone, you're just left with a single integral, you have the exact formula that you would have used back when you learned how to find the area between two curves in a previous calculus class. What to say? It's been a long term. We started with vectors, we did lines and planes, vector valued functions, not polar coordinates, but parametric functions, power series, partial derivatives, now double integrals. Covered a lot of ground. And I hope that you can see some of the beautiful and amazing ways that calculus can be applied, the ways we can extend it out of 2 dimensions into 3 dimensions, maybe even get hints of beyond. You learn some powerful tools like vectors that are going to come up in a variety of places. You learn some of the tools that Newton and Leibniz themselves used with power series. So much here. So much to be thankful for. I'm so glad to have been able to spend these last videos sharing with you, talking about calculus with you. I hope it's been as wonderful an experience for you as it has been for me. And I also hope that you have the pleasure of continuing your studies in calculus and seeing what else can be done um, with double and later triple integrals in vector calculus, because it's just a beautiful thing to see all of these topics come together with the nice, neat bow tie that is the Green's theorem, Stokes' theorem, and the divergence theorem. But in the meantime, we just enjoy the beautiful work that we've been able to do and enjoy the beautiful time together. Thanks so much for the wonderful term. Take care, and I'll see you next time, if there is a next time.